Hello. Can you hear me?
Yeah,
Okay, can you see my shared screen?
yeah, you already shared the screen, Prof.
Is that okay?
Yeah, it's okay. Uh, okay, Bismillah Rahman Rahim. Assalamu alaikum wa rahmatullahi wa barakatuhu. I welcome you all to this first technical session. We have two speakers scheduled for this session. I request all participants to, we'll have a 10 minutes question answer session at the end of the, when the speaker finishes the session. And participants are all requested to pose the questions specifically in the question answer chat box. So to begin with, our first speaker for the session is Professor Zhang Fan. Professor Fan is currently a professor at the Institute of Tibetan Plateau Research, Chinese Academy of Science. She's a serving associate editor for the Journal of Hydrological Engineering Science and the science editor for the Journal of Mountain Science. Professor Fan got her BS and MS degree from the Tsinghua University in 1998 and 2000 respectively, and a PhD degree from the University of Central Florida in 2005. She worked for the Environmental Science Division at the Oak Research National Laboratories and the Research Associate and then the Research Staff Scientist during 2005-2009. Dr. Fan, research focuses on the watershed hydrology, erosion, sediment transport, and the refractive transport modeling. Professor Fan has more than 70 research publications and a book entitled Groundwater Refractive Transport Models. She's the member of various professional organizations that include Eco-Hydrological Committee, Ecological Society of China. She's the member of Soil Physics Committee, Soil Sciences Society of China. She's the editorial member of Water Security. She's the editorial member of the International Soil and Water Conservation. She's the editorial member of Journal of Water Resource and Protection. She's the science editor of Journal of Mountain Science, also an associate editor of Journal of Hydrological Engineering. With these brief introductory remarks, I welcome Professor Fan to deliver her invited talk. The title of her talk is Climate Change Impact on the Riverine Runoff and Sediment Flux over Tibetan Plateau. Professor Fan.
Okay, hello everyone. Good morning or good afternoon. First of all, I'd like to thank the Department of Environmental Science, University of Kashmir for the invitation to participate this webinar. And today I would like to take this opportunity to share our progress on the climate change impact on riverine runoff and sediment flux over the Tibetan Plateau. My talk will be about 30 to 35 minutes, which will leave us a little bit more time for discussion or maybe break. Here is the outline of my presentation. First, I'd like to briefly introduce the background of the riverine runoff and sediment flux study, especially in the Tibetan Plateau. Study on the patterns and changes of riverine runoff and sediment flux has always been a hot issue for the Earth system science study. Many studies have been carried out for major rivers all over the world. Among this study, Professor Walling from the United Kingdom and his colleague analyzed the changes in sediment flux of 145 major rivers since the 1950s all over the world. Among these rivers, it was found that nearly half of the rivers showed significant decreasing trends in sediment flux. And this mainly resulted from the soil and water conservation and sediment control measures, as well as the retention by the reservoirs. The sediment fluxes of the other half of these rivers have no significant changing trend during the time. And in these river basins, maybe the controlling factors have no significant changes. All it is resulted from the combined impact of the positive and negative influences. While only A very small portion of these rivers, that is only about 5% of the rivers, showed a significant increasing trend of sediment flux. And the reason may be the surface disturbances such as logging and mining, or it may be resulted from the climate change. As we know, most of the hydrological stations are distributed in the middle or lower uh, stream of the large rivers. So most of these relevant studies focus on the downstream of large rivers, which is always under the intensive influence of human activities. Therefore, isolated impact of climate change on riverine sediment transport remains poorly understood due to the limited data and analysis. The Tibetan Plateau, as we know, is also called the Asian Water Tower. It has a total glacier area of about 100,000 square kilometers and a total lake area of about 50,000 kilometers. It is the headwater of more than 10 large rivers in Asia, and these rivers provide precious water resources for more than 2 billion people in total in these basins. And also this river also transport about 1/3 of the sediment flux uh, to the oceans. So the rivers originated in the Tibetan Plateau are not only important water resources, but also important marine sediment transporter as the global geochemical cycles. The special physical graphical condition in the Tibetan Plateau make the soil poorly developed in this region, resulting thin soil layer. But this thin soil layer is subject to multi types of erosion, such as those driven by water flow, wind, or the freezing thawing cycles. Riverine sediment flux um, is considered as an important indicator of soil erosion changes and the influence of climate change due to the limited human activities in this region. In addition to that, during the last 60 years, as indicated by the right-hand figure, the warming rate recorded by the meteorological data in the Tibetan Plateau is almost twice as large as the global average. Therefore, it is also a region subject to serious global warming impact. In order to understand the runoff and sediment transport processes over this region, this study first investigated the overall spatial pattern of runoffs and sediment flux. As we shown here, the headwater area of 8 major rivers with long-term observation were selected to study the riverine runoff and sediment flux. These rivers include the Yangkang River in the west, the Shula River and Heihe River in the north, the Yellow River, Yangtze River, Lancang River and Nujiang River in the east, and the Yaluzangbu River in the south. The data of hydrological stations shown as the blue triangles in this figure are used to calculate the runoff and suspended sediment flux, while the data of meteorological stations indicated by the red dots in the plot are used to calculate the average air temperature and precipitation within each basin. Here we show the proportion of major land use types in these 8 headwater river basins, where the green color represents the grassland and the yellow color represents unused land, which is mainly bare land without vegetation cover or construction area. From this plot, we can see that the land use type in the headwater basins is mainly grassland, except for 2 river basins. One is Yangkang River and the other is Shula River. In these 2 river basins, the land cover is dominated by unused land. And here this plot indicates the amount of precipitation, the runoff, and the sediment flux of these 8 headwater basins. We can see that the rankings of precipitation, runoff, and sediment flux are quite different among different headwater basins. For example, if we look at the Yangkang River, um, the precipitation of this river basin is very small, and it is ranked as the smallest among the 8 basins, while the runoff of this basin ranked among the middle of the 8 rivers, and the sediment flux is much higher and is the second largest among 8 rivers. So these different rankings indicate the complexity of runoff generation and the sediment transport processes over the Tibetan Plateau, which is not only supplied by precipitation or rainfall, but also supplied with snow and glacier melt. In order to eliminate the impact of the river basin area difference, runoff depths and the sediment yield of each basin were further analyzed. The runoff depth is calculated as the runoff divided by the catchment area. Similarly, the sediment yield is calculated by the sediment flux divided by the catchment area. And the statistical analysis shows that runoff depths in these 8 headwater rivers is positively correlated with precipitation, but negatively correlated with the permafrost area ratio in the basin. The plot on the right-hand side compared the runoff depths of these rivers with their major influencing factors, in which the orange represent permafrost area ratio in these river basins. The dark blue represent the runoff depths, and the light blue represent precipitation. The headwater of 3 rivers, Yangtze River, Shula River, and Heihe River, where the permafrost area account for a relatively large ratios, have smaller runoff depths. And among these 3 basins, the larger the permafrost area ratio, the smaller the runoff depths. Well, for the other 5 basins with relatively small permafrost area ratios, they have larger runoff depths. And among these 5 basins, the greater the precipitation, the greater the runoff depth, which is easy to understand because the precipitation is major water supply in these rivers. According to previous study, in permafrost regions, although the thawing of shallow soil in summer may release some frozen water to supply the runoff, it mainly inhibited the runoff generation due to the increase of active layer thickness and soil water storage capacity. Compared with the runoff depths, the factors affecting sediment yield seems to be more complex. Statistical analysis shows that sediment flux, sediment yield is positively correlated with runoff depths, glacier area ratio, river channel gradient, and air temperature, but negatively correlated with grassland ratio. The plot on the right-hand side compared the sediment yield with 2 major factors, where the light blue represents the glacier area ratio, the brown color represents sediment flux, and the dark blue represents runoff depths. It can be seen that the headwater basin of Yangkang River and Shula River with largest glacier area ratios have the largest sediment yield. And this pattern actually is consistent with previous studies in alpine regions, which shown that sediment yield of glacier-fed catchment is most often larger than those exposed to flow erosion only. Well, for the other headwater river basins, accounting for smaller glacial area ratios. Sediment yields are smaller, and among these basins, the higher the runoff depths, the higher the sediment yield. So the above comparison among different headwater basins showed that sediment yield of Alpine River Basin can be affected by multi-factors, such as topography, climate condition, land use, and so on. In addition to that, we also analyzed the spatial pattern of sediment transport within the basin of Yaluzangbu River, which is the longest river in Tibet, and it is also the upstream of the Brahmaputra. Schematic map of sediment flux along the Yaluzangbu River with contribution of major tributaries are shown here. From this plot, we can see that the midstream segment between the Lazi and Yangcun hydrological stations is the major erosion zone, while the White Valley segment between Yangcun and the Nuxia hydrological stations is an important sedimentary zone. According to the research of Professor Zhao Yingwang from Tsinghua University, the river channel has a lotus route looking with alternating canyons as narrow as 200 meters, but wet valleys as large as 10 kilometers. So when the river flows through the wet valleys, the flow velocity slows down, and the sediment carrying capacity of the water flow decreases sharply. So large amount of sediment can be settled down, resulting in reduced sediment flux in the downstream. These results further indicate the impact of topography on river sediment transport. In addition to the sediment flux variation along the mainstream, it is interesting to see the contrast between two midstream tributaries. One is the Lhasa River in the east with higher runoff supplies but lower sediment flux, and the other is the Nianchu River in the west with lower runoff supplies but higher sediment flux. To understand the contrast between these two rivers, we use the RUSLE model to calculate the soil erosion rate and its influencing factors. As shown in this slide, the left-hand side figure indicate the spatial variation of precipitation and the vegetation index NDVI. They both show the slightly decreasing pattern from east to west, which explain the higher runoff in the Lhasa River than the Nianchu River. And compared to the spatial patterns of different patterns, the soil erosion rate as indicated by the right lower corner panel show the high soil erosion rate in the west compared to the east. And this pattern was mainly consistent with that of soil erodibility factor. This indicates that the higher sediment flux from the Nianchu River is mainly resulted from the higher soil erodibility factor. Based on the analysis of the spatial pattern of runoff depths and sediment yield, we further investigate the variation of runoff and sediment flux over the Tibetan Plateau. Here, we show the time series data of the annual runoff from these 8 headwater rivers during the last 60 years. It is seen that the annual runoff variation is kind of moderate, with anomaly ranging from -50% to 80%. In comparison, this slide shows the annual sediment flux anomaly during the same period. We can see the anomaly ranges from -100 to 420%, which is much larger than that of the annual runoff. This comparison indicates that the riverine sediment transport was more sensitive to climate and environmental changes than the runoff. To further analyze the potential factors influencing the runoff and sediment flux changes, Mankando and Pettit analysis was performed. The results show that temperature of the 8 headwater basins all showed significant increasing trends, while the precipitation, runoff, and sediment flux showed varied trends in different river basins. And Spearman tests indicate sediment flux of these 8 rivers were all significantly correlated with runoff, but the correlation between sediment flux and temperature or precipitation was different. And in order to further analyze, we divide the 8 rivers into 2 groups. One group, including the headwater of Yangkang River, Shulo River, Hehe River, and Nujiang River, shows significant increasing trends in runoff and sediment flux. And this group of river has relatively larger glacier area ratio. Among these 4 rivers, except for the Hehe River with the smallest glacier area ratio, sediment flux of the other 3 rivers were all positively correlated with air temperature. This indicates that the changes of runoff and sediment flux were influenced by the increase of meltwater caused by air temperature rise and the change of precipitation. The other group of the river include the Yaluzangbu River, the Yellow River, Yangtze River, and Lancang River. This group of rivers shows non-significant changing trends in runoff and sediment flux during the same time period. And this group of rivers have lower glacier area ratios. The correlation tests indicate that there is no significant correlation between sediment flux and temperature in these 4 rivers, but they mostly show significant positive correlation with the sediment flux, between the sediment flux and precipitation. Therefore, in the river basins with small glacier area ratio, precipitation played a major role in the runoff and sediment flux process. There is a special case for the headwater of Yangtze River. In this basin, although precipitation increased significantly, however, because this river basin have relatively large water area, that means the storage capacity of lakes and marshes may buffer the changes. A further study on the Toto River, which is the most upstream part of the Yangtze River headwater, has revealed some significant changes. According to the analysis in the past 30 years, when the continuous observation data is available, air temperature, precipitation, ground temperature, runoff, sediment concentration, and sediment flux, all these variables show significant increasing trend, which was mainly due to the stepwise increase around 1997. Since before the 1997 or after the 1998, the changing rate of these variables are much lower than the overall changing rate during the whole time period. To identify the potential mechanism of the changes, we first use the double mass plot to analyze the relationship between different variables. And this plot indicates that both meltwater and rainfall contributed to the increased river runoff, while the increased sediment flux mostly resulted from enhanced erosion power and transport capacity of the increased runoff. But this increase was kind of buffered by a decrease in the sediment source due to the shift of monthly rainfall from June, July to June, August, when, um, when a denser vegetation cover prevent the soil from intensive erosion. A partial least square structure equation modeling was further performed to analyze the relationship between different variables. And this analysis result confirmed the dominance of warming on the increase of runoff, which is also amplified by the increased precipitation. It also confirmed that increased precipitation drives the increase in suspended sediment concentration, and the increase in both runoff and suspended sediment concentration contribute to the stepwise increase in the sediment flux. So the above results indicate the runoff changes in these alpine rivers will further drive the sediment flux change. So the impact of climate change on alpine river runoff were further investigated. Here, 3 basins of different glacier area ratio were selected to carry out the snow and runoff simulation. And based on the simulation of glacier runoff, snowmelt runoff, and rainfall runoff components in these basins, the influencing mechanism of glacier area ratio on the Alpine river runoff changes was identified. First, the results showed that the major component of runoff has changed from glacier and snowmelt runoff to rainfall runoff as glacier area ratio decreased. And this also led to a shift of glacier and snowmelt runoff peak from summer to late spring. In addition to that, the response of runoff to temperature and the precipitation changes were also different when with different glacier ratios. For the Kaohsiung River, shown in the bottom with the highest glacier area ratio, the increase in temperature will cause increase of meltwater runoff, which dominate the runoff changes. While for the other 2 rivers, which has much lower glacier ratio, the changing trend of runoff was dominated by the changing trend of precipitation instead. So to sum up, for this section, the climate change impact on the riverine runoff and sediment flux depends heavily on the glacier coverage in individual river basins. Based on the above results, I would like to briefly discuss the uncertainties of riverine sediment flux change over the Tibetan Plateau. The sediment transport process over the Tibetan Plateau was affected by various climate and land surface factors. This figure illustrates the potential effect of different factors on the sediment flux, where the climate factors affecting sediment flux mainly included temperature and precipitation, and the factors the land surface process factors mainly include glacier, frozen soil, vegetation coverage, glacier runoff, snowmelt runoff, and rainfall runoff. Because our study area is located at the south or very upstream of these rivers, which was slightly influenced by human activities, the impact of human activity was not discussed here. Again, let's look at this figure. The increase of temperature leads to the increase of meltwater and at the same time the degradation of frozen soil. While the increase of meltwater and rainfall will both enhance the erosivity and sediment transport capacity of rivers. Soil freezing and thawing affect both the runoff generation and the erodibility of surface soil through seasonal or daily freezing and thawing cycles. Generally, temperature, precipitation, and glacier runoff are considered as the positive or the enhancing factors to increase the river sediment flux, while the vegetations are considered to be buffering factors to reduce the soil loss. At present, the impact of climate change on frozen soil and the impact of frozen soil change on runoff generation and soil erosion processes was still not clear. In addition to the impact of different factors, the Tibetan Plateau has shown a warming rate, as we mentioned, almost double the global average. And also it has an overall humidifying trend, which lead to the glacier retreat, glacier runoff increase, and permafrost degradation as a whole. But at the same time, the plateau ecology is generally getting better. The vegetation coverage index is generally increasing. However, due to the weakening of Indian monsoon and the strengthening of westerlies, there are obvious spatial patterns in the changing trend of different climate and land surface factors. For example, precipitation tends to increase in the north but decrease in the south. Glaciers are mostly retreating in the Tibetan Plateau, but remains stable or even advancing in the west. Therefore, to understand the change in sediment flux and the response to climate change, it is also needed to consider the special patterns of different climate and land surface process variables. And this all add up to the uncertainty of the sediment flux changes over the Tibetan Plateau. In the end, I would like to give some example about the influence of riverine sediment changes to call future attention on the relevant study for adaptation purpose. The riverine, as we know, soil and grass serve as the basis for agriculture and husbandry over the Tibetan Plateau and is critical for the local people. So, considering the riverine sediment flux change over the Tibetan Plateau, which have caused a series of ecological environmental risks, the first is the soil and the grassland degradation caused by soil erosion. For example, in the middle reach of Yalozambu River, due to soil erosion, gully bank expansion, and flash floods, the cultivated land in this region has been washed out to or submerged to very degrees and causing cultivated layer to become shallower and the soil fertilities to decline. Another aspect of the influence is the segmentation of river channel and reservoirs and sediment deposition in the riverbed, especially the massive deposition caused by flood event, will cause the riverbed to rise and narrow the cross-section, which will affect the river flow transportation and the flood runoff capacity. Taking the Nianchu River as an example, the riverbed siltation is one of most important reasons for the frequent flow cutoff and flood events in recent years. In addition to that, sediment deposited in the riverbed can be a major source of dust weather in winter and spring. For example, in the valley area of midstream of Yalozambu River, after the water level drops in the dry season, sandstorm can be formed under strong wind, and these sandstorms forces the Lhasa Gonga airport to close intermittently for dozens of times every year. Another aspect of the influence is on the safety and operation of hydropower project. As we know, riverine sediment flux is an important factor that must be considered in the construction and operation of hydropower project. The safe operation of this project not only need to consider the current level of sediment flux, but also need to pay attention to the changes in the riverine sediment flux under the climate change impact. So to sum up, here are some major conclusions from today's presentation. First, the comparison of headwater areas shows that runoff depth is positively correlated with precipitation, but negatively correlated with permafrost area ratio. The sediment yield is more complex, and it is positively correlated with runoff depth, glacier area ratio, river channel slope, air temperature, but negatively correlated with grassland area ratio of the basin. In the past 60 years, the changing trends of sediment flux of the major rivers in the Tibetan Plateau is different from the main rivers in the world. Among the 8 rivers with long-term monitoring, sediment flux of half of them has increased significantly, indicating the impact of climate change. The positive and negative impact of multi-factors such as temperature, precipitation, glaciers, frozen soil, vegetation, and their spatial patterns lead to the complexity and uncertainty of sediment flux changes and caused a series of risks which need further attention for the future study. This is almost all for my presentation today. And here I listed the recent publications which are the basis for today's presentation. And I would also like to acknowledge the contribution of co-authors of these papers for the presentation. So that's it. Thank you all for your attention.
Thank you, Professor Fan, for this wonderful and comprehensive insight on the climate change impact on the riverine runoff and sediment flux over Tibetan Plateau. So I may invite some questions, some quick questions. We have a question from Dr. Arshid Jahangir in the chat box. And Dr. Arshid is asking what is the percent cover in the Tibetan Plateau and how the vegetation cover can be increased in order to prevent the sediment runoff, and what type of a vegetation can be grown as a higher altitude and the cold conditions can limit the vegetation types.
Okay, this is a very interesting question, but as a hydrologist, I may not provide a very good answer for that. According to my knowledge, the vegetation cover in the plateau actually varies or shows great spatial variation from west to east because the precipitation of the rainfall shows great spatial variation. So it is difficult to see what's the vegetation cover in the Tibetan Plateau due to the large variation. Related to what type of vegetation can be grown, it is very difficult, especially in an alpine area with harsh climate condition and with very limited population. But still, there are some projects to investigate this problem. So it is in the stage of research. Yeah, that's what I know.
Yeah. Thank you. There's one more question from Rinchen Angmo. He's asking, does the riverine and sediment flux affect the animal or ecology, and to what extent?
I think that for sure that will influence both the water environment and the ecology. For example, if the sediment concentration in the river becomes too high or suddenly become too high due to, for example, the glacier collapse or some other disasters, the increased concentration of suspended sediment will affect the light penetrating into the water, and that will influence the fishes in the water. And if it becomes more serious, it will even influence the birds living surrounding the water. So the suspended sediment concentration actually is one kind of variable for the water quality evaluation. So sediment transport will surely influence the water physical property. In addition to that, sediment is also a carrier for particulate chemicals. For example, the mercury is a special type of contaminant that may transport in form of particulate, not in the dissolved phase. So the suspended sediment concentration will also influence the transport of this type of pollutants, or this type of or other type of nutrients in the particulate form.
Okay, so there's one more question from Mr. Ahmed Ali, and he's asking how much temperature has increased since the last decade in Tibetan Plateau.
Yeah, actually, as I mentioned, the warming rate in the Tibetan Plateau is almost doubling the global average. For example, if we expect the global average temperature to increase 2 degrees Celsius in the future, the situation in the Tibetan Plateau could be 4 degrees Celsius. This will have serious impact on the vegetation and soil ecology. And at the beginning, the increased temperature will enhance the vegetation growth, but it is limited by the soil moisture or the precipitation condition. So at the beginning, it will enhance the vegetation growth, but when the situation is limited by the moisture, the further rising of temperature may not enhance the vegetation growth anymore. These are just some preliminary results.
Yeah, he's adding some more like impact on vegetation and soil that I believe you have already answered. There's one more question by Mr. Sharjeel Sofir, a scholar from the Department of Environmental Science, and he's asking what would be the impact for flow alterations on the ecological health of the rivers.
I'm sorry, I don't see these words. Can you say that again?
Yeah, what would be the impact of a flow alteration on the ecological health of the rivers? Alteration of the flow.
Sorry, I still don't get the.
Yeah, like it's like asking like change in the hydrology. How is it impacting the ecological health of the rivers? How does it impact the ecological health of the rivers?
I think for that aspect, I don't really have experience about that. Yeah. I think it's some research area need to be touched in the future.
Yeah, there's one more question from Mr. Sharjeel. He's asking that can you please throw some light on the sustainable sediment strategies for the river subject to fragmentation by the hydropower plants?
So as I mentioned, considering the operation of hydropower plants, for example, the initial design must be based on some historical data about the sediment flux. However, considering the serious impact of climate change on the sediment flux changes over the Tibetan Plateau, the variation should also be considered. Otherwise, maybe the operation length of the project could be much shorter than the expectation.
So we do have one more question from Dr. Samiullah, and he's asking like, do we have a comprehensive study available on the impact of a sediment on the fishes in Tibetan Plateau? The impact of a sediment flux on the fishes?
I'm not quite sure. As a hydrologist, maybe it's some area I'm not quite familiar with. Yeah, I can understand that you must be very care about that, considering the topic of today's meeting. But I'm sorry, I'm not an expertise in that part.
Okay, there's one more question from Mr. Irshad, and he's asking about the uncertainty of the hydrological models. You know, when we talk about the Kashmir Himalayan region, we don't have a continuous monitoring here. We don't have a network of the stations here. So in that context, how good or how bad are the gridded, data sets that are available for the region, in terms of perfectly simulating the hydrologic conditions?
That's very interesting question that we have been paying attention to during the last 10 years. Even though for us, we may have some hydrological station data, but it's very limited. Yeah, but in order to reduce the uncertainty in the hydrological modeling, we have used multi-source of data. For example, in order to do the parameter estimation for snow-related parameters, we use the remote sensing snow cover area data for model calibration. And sometimes in order to estimate the soil-related parameters, we may use the remote sensing land surface area temperature for model calibration also. And sometimes some field investigation about glacier mass balance can be used to determine the glacial melt parameters. To sum up, we use different ways for model calibration and for model parameter determination to reduce the uncertainty in the hydrological modeling. And another way for the runoff estimation is use the remote sensing methodology and to build some relationship between the runoff and the river channel geometry parameters like the river widths or other parameters.
Yeah, ma'am. Your answer brings me to another question. I mean, it's on my behalf. Like when we talk about the remote sensing in terms of mapping the glacial map, we do have a limited ability in terms of perfect glacial mass balance. So doesn't it compromise on how we simulate the hydrological models and how we predict through the hydrological models then? Because when we talk about the glacial mass balance, monitoring the glacial, we do are limited in terms of perfect mass balance, determining the perfect mass balance.
So related to that, in our institute, we emphasize on the in situ monitoring of glacier mass balance in different glaciers, because in different locations of the Tibetan Plateau, the glacier mass balance could be quite different. So we still emphasize on the in situ observation.
Yeah, thank you, ma'am. There's one more question from Ms. Mahin Javed, and she's asking that is there any alternative method for the estimation of a sediment acceleration rate in addition to a radioisotope method?
I think in addition to hydrological station data, there is another type of data, is the lake sediment core data. In the lake basins, because most of sediment will enter the lake and settle down. So the lake core sediment data can also provide the kind of sedimentation rate during a long time period, which also can tell us the changing rate of sediment transport. So this is the other type of data I have known from the literatures, even though I haven't worked on those type of data by myself.
So there's one more question by Mir Muzaffar. He's asking how water scarcity can be solved in the upper east, hilly areas, and what are the best methods to harvest the rainwater?
I'm sorry again, can you repeat that question?
There's one more question is there any by
Oh,
Miss
how
Reen
water
Akhtar?
scarcity can be solved in upper reaches, hilly
Yes.
areas. What the best method to harvest the rainwater? Oh, that's a very good question. Yeah, I think that is related to water use and policies.
Yes.
Yeah, I'm not quite good in that area either. Yeah, but I think for the limited water resources, I think preventing water pollution is very important aspect to make good use of the precious water resources.
Yes, there's one more question from Ms. Zarina Akhtar. She's asking, like, is there any research work regarding the sediment impact on the ecologically important bottom dwelling organisms?
Yeah, again, yeah, as I mentioned earlier, related to this type of questions, I'm really not an expertise.
Okay, ma'am. To conclude the session, we'd like to have a message from you, any special message that you want to convey to, yeah, for the research purpose, to convey to all research scholars and all the participants.
I'm sorry?
Yeah, to conclude, we request you to give us some, some message, any thoughts from your end for research scholars at the University of Kashmir, or all the participants that are joining the conference.
Uh, yeah. First, I want to express my appreciation for the invitation for this event again, and I'm glad to share our research progress with the colleagues. And we also hope to build future collaboration, because we all live in the mountain area, and we may facing the same problem. And so yeah, I really looking forward for future collaboration in this aspect. Thanks again.
Thank you very much. Thank you, Professor Fan, for this, for accepting our invitation and delivering this wonderful talk. Thank you very much.
Thank you. Thank you.
So we do have our second speaker on board now. Our second speaker for the session is Professor Basant Maheshwari. Professor Maheshwari is currently the professor at the Water, Environment and Sustainability, West Sydney University, Hawkesbury campus, Australia. Professor Maheshwari has done his BE in Agriculture from University of Udaipur, Masters in Soil and Water Engineering from East Institute of Technology, Bangkok, and PhD in Water Resource Management from the University of Melbourne. Professor Maheshwari has over 25 years of professional experience in research, teaching, consulting and development works related to the range of water-related issues and challenges, including water recycling, environmental hydrology, and the urban irrigation management. During the last 10 years, his work has focused on peri-urban water and its interactions with the landscape, and involving modeling and analyzing water cycle for a long-term water resource planning at the regional level. His works also include engaging community, government agencies, and other stakeholders to tackle significant local water issues and developing a tool and strategies to enhance regional water security. He's currently leading a transdisciplinary research and the development projects in India called MARVI, managing groundwater use and aquifer recharge through the village level intervention. The project is funded by the Australian Centre for Agriculture Research. Professor Maheshwari has more than 210 publications, including 80 articles in the peer-reviewed international journals. He is the recipient of various national and international awards that include Fellow of Indian Society for Agricultural Engineering, Collaboration and the Leadership Award from CRC for Irrigation Future in 2010, Vice Chancellor's Excellent Award highly commended individual for university engagement in the water research in the same area in 2010. Vice Chancellor's Award for the excellent commended team for the university engagement through water and irrigation strategies enhancement through the regional partnership WISER project in 2009, and the outcome award from CRC for the irrigation future in 2005. With this brief introduction, I welcome Professor Maheshwari to deliver his invited talk. Professor Maheshwari will be talking about the managing the invisible resource, participatory groundwater monitoring and management through MARVI approach. Professor Maheshwari, please.
Thank you very much for your kind introduction. And it is a great pleasure to be here and to deliver this talk. Also, thanks to Dr. Bhatt for inviting me, and also acknowledge all the uh, participants and the key people here. So I would like to share the screen here. And also, before I do that, all the best wishes to everyone on this World Water Day. It's very auspicious day in those who value and respect water. Um, we have a very difficult situation at the moment in Sydney. Very heavy rainfall in last 2 days, more than 300 millimeter rainfall, and it's flooded everywhere, and people are in big trouble on the World Water Day. So it's again another special reminder that water can be source of um, help, and also it's a natural thing, the floods and droughts. So this is what is water. Uh, so our campus is closed for indefinite period. All the schools are closed. So it's a very different day. So anyway, so welcome. I would like to share the screen. Okay. So thank you. So I would like to talk to you about this project called MARVI, which is managing aquifer recharge and sustaining groundwater use through village level intervention. So start here. And when we talk about groundwater, it's something underground. So it's not visible, it's invisible. And when we compare with surface water, so surface water we can see in the dam or lake or river or like that, but we can't see the underground water, and also the flow cannot be controlled. And also the pumping is hard to monitor, especially in country like India. And the problem of the groundwater is excessive use of groundwater. So we are using more than what is recharged every year. So it's like a bank. So if we spend more money out of our bank account, we will run out of the money. And same is happening with groundwater. The other aspect of groundwater is it is a decentralized resource, and so its ineffective management is very much a problem. And also the government, not only in India but in other places, also low level of investment. So we only realize the problem when the well runs dry. Very famous uh, quote from Roosevelt, Franklin Roosevelt. So now slowly, I think in India also it is being recognized that this through Atal Bhujal Yojana, for example. So now government is looking into this. And the I think the important part is groundwater is very, very important because we get rainfall only for 30, 40 days in a year. Rest all depends on bit of surface water, but lot of groundwater. So Indian agriculture depends on groundwater 60% or more water used in irrigation is groundwater. More than 80% of drinking water in villages comes from groundwater. Many industries depend on groundwater. And when there is no groundwater left or very little, it will affect the uh, livelihood, what we do, what we can do. So, the whole idea of the water resource development and management has gone through different phases. So, the production phase, which was, say, early, soon after independence, 1950s, 60s, 50s. So, the focus was on using as much water as possible. So, build dams everywhere, anywhere, as long as there's money and site there. So, we built many dams, which was good because the country got started in economic development. And then soon we realized that we're running out of the storage. And then came the productivities. How can we produce more out of given volume, given cubic meter of water? So that's the productivity. So that was through um, improved varieties. If you talk about agriculture, improved varieties or improved method of irrigation, better irrigation management, water conservation. So that was good. Then, so in 70s, 80s, it was more focus on productivity. And then 90s, we started thinking, okay, we can't do much more. It's very, there's a law of diminishing return. So there's a limit how much you can be productive. The productivity got a limit uh, because of various constraints. And then we started, can we continue the use, the sustainability? Can we continue the groundwater, water resource use for next 20 years, 50 years, whatever? So sustainability. And sustainability, you start thinking social, economic, environmental, all those things. So can we sustain water use? And we also getting to a limit now, and we are now talking about water security. So will we have water in 5 years time or 10 years time or like that? So that is also becoming now very important. So we have gone through these phases of water resource planning, management, development. And so the challenge of groundwater is it's an invisible resource, and when something is invisible, it is hard to communicate. So even say we've gone through this pandemic, so this virus is not visible and to everyone, and so it's very hard to say what is happening, what can happen. And this is one of the challenges with the groundwater science and management. So because we don't know which way the water will flow, especially in hard rock areas, and also the managing this resource being invisible is not easy. And also another issue with groundwater is a common pool resource, means it is everywhere underground, so it belongs to everybody and everyone wants it. So any common land, for example, so everyone wants to the playground, for example, public space. Everyone wants to play there, go there, but no one wants to take care and responsibility. When that happens, then we are in trouble actually. So we need to change that aspect if we really want to have this common pool resource uh, to sustain, be still useful. And if that doesn't happen, then we have this tragedy of commons, which is very well research area. If there is a common resource, and we often come to a point where we have this tragedy. So if we go back how the groundwater is used, so some younger people probably don't recognize these things, but on the left side, this is called rahat or Persian wheel. So you have this thing rotating and you pulling pulling or lifting water out of a well. Then you have to have it this charas or the water bucket, pair of bullocks pulling out. Very traditional, very uh, simple method, and it was useful. And then came these pumps. So what these farmers used to do in a whole day, these pumps can do in half an hour. So what does that mean? The groundwater started depleting. So we started using more than what is recharged every year. And when that started happening, the level went down, and people start digging more, deeper, then digging deeper. Still, they are running out of water, and then they started drilling horizontally. That also has a limit. And they went then these drilling machines on the left, so you can go up to so dug wells, open wells, you can go up to 30, 40 meters. After that, it's very hard to dig any further. It requires a lot of money and this thing. But then these drilling machines came in, and you can go 500 meters, 300 meters, even 1,000 meters. In Bangalore, I saw some wells. They said we are pumping water from about 3,000 feet, which is 1,000 meter nearly. So we really started emptying the aquifers, and not only aquifers, very very old water. Some water could be hundreds of year old, because as you go deeper, groundwater, there's a fresh groundwater, and there is a fossil groundwater, very deep groundwater, which was recharged and occurred long time ago. So this is the problem. This is how whole thing changed, the whole scenario changed. So what is happening? There is a need and there is a demand. There is a demand here, and there is a supply, which is annual recharge. So only way groundwater becomes available to us is through recharge, through rainfall recharge. There is no other way. Groundwater is not produced underground, only that way. So we have different uses of groundwater. So drinking water we require, industries require, and environment also requires, because environment, when we talk about environment, we talk about trees, we talk about river, we talk about other animals, and so whole ecosystem, and that also requires water. And groundwater is a big source of water, because if you see big deep rooted trees, for example, they survive on groundwater. So in my village in Rajasthan, I used to see lots of mango trees, but they all of a sudden started dying because the groundwater went deep and there was not much water available to survive. And so it happens if groundwater goes deeper, that things can happen. And some of the rivers flow because of the groundwater. So there is no rainfall, but some river keep flowing throughout the year, or creeks that comes through groundwater. So very important. And the best of all is the agriculture. 60-70% of water is agriculture. So if groundwater is in trouble, agriculture will be in trouble. Our food security will be in trouble. So what ideally we would like to do is the demand or use equals the supply. If we can do that, we are in a safe position. But even better, if we can have more recharge and less demand or less use, then we have a guaranteed sustainable use of groundwater. And that requires a lot of rethinking, a lot of how we use, how we recharge groundwater. And water problem is much more complex. So when we were in the production phase, or we were thinking about water for collect as much water as you want and you can use as much as you like. But when that part is finished, and also now the water is no more a physical resource. It's not just H2O. It has got implications for livelihood, implications for jobs, human needs, and so we need to think differently. We need a different type of solution to sustain groundwater. So groundwater is like an elephant, and so there are different parts to elephant. So the government says I can regulate and make policies, and then hydrogeologists or hydrologists say I can tell you where the water is, and researchers say I can explain to you exactly what is happening, and then bank or financiers can say I can give you the money and you go and drill deeper and you have the groundwater. And similarly, farmers say I need to pump as much as what I want because I want to grow crops. And drillers says I can drill deeper. So these are very limited interest groups or people. And so no one is working together. No one is thinking about the elephant. It's just the parts of the elephant. And that is where the problem is. So we need to bring everybody together to sustain groundwater, to not make this elephant extinct. So, what are the options to sustain groundwater? One might say we need to improve irrigation efficiency. So, we are more efficient user of water. That's very good. We need to change to crop that requires less water. That is also very good because then you save water. And we can say we can recharge more groundwater. So there is more water in the aquifer. But will that lead to sustainability? Not necessarily. Because if you have more groundwater, because we are sort of people, if there's something more, we want to use more. So people will, if they are operating pump for say 6 hours, they will go for 8 hours or 10 hours. So they will pump out more water. They will, if they are growing one crop, they will grow two crops. And so people will keep pumping out or using groundwater until it is exhausted. The aquifer is exhausted, and this is what is happening. So controlling, conserving water will not solve the problem, but we need to change the whole thinking. We need to engage and help people and users so that they take the responsibility of the problem and also the solution. So it doesn't become, say, somebody's problem and somebody's solution, but it becomes the user's problem and user's solution. So that's where this Marvi project came in, managing aquifer recharge and sustaining groundwater use through village level intervention. So I just want to highlight what were the learnings we achieved through Marvi. So one of the aspects we learned is groundwater scarcity is people related problem. And this is related to our greed, lack of understanding, and in being it's being invisible resource. So lack of understanding, say we talk to farmers and they think groundwater, there's an underground river flowing. So if you go deeper, there's more chance of getting more water. But that's not true. To succeed in this sort of complex problem, the solution need to start with people. And for people to start working on the solution, they need to be engaged, they need to be empowered with the knowledge, with the experience, and they need to develop this village level groundwater science. So we have learned science in the university and we know equations and all those things. So that's very good. But really, we need some science that people, farmers can use, village level people can use, understand, and act on this. So we need to engage people at all levels, whether it's a farmer, community, school, government agencies, politicians, even. So we need to talk about this whole idea of groundwater management, sustainability. And also, we found that the level of formal education is not a problem. It's not a barrier to learn about groundwater science. So, some of the people were only we had were primary education had a only primary education. They were able to because they had a life experience. They understand, and they were able to grasp and act on this. So what we had in this Marvi project, 9 organizations: Western Sydney University Development Support Center in Ahmedabad, Arid Communities and Technologies in Bhuj, Gujarat, Maharana Pratap University of Agriculture and Technology, Vidya Bhavan Krishi Vigyan Kendra, both from Udaipur, and then the Australian partner CSIR or Land and Water, International Water Management Institutes. Then we had two other partners, Mekong Region Futures Institute in Laos and Carnegie Mellon University based in South Australia. So altogether, we had 30 researchers. Also, we had 35 farmer researchers, and we called them BJs, for short Bujal Jankars. So, and this project has been running for last 9 years. So, what activities we did in Marvi? So, spending a lot of time in the villages, and it's a participated data collection. So, these village people collected data on groundwater depth, rainfall, water quality, water levels in check dams, and then we shared this information, or they shared rather, and tried to understand what is happening, and also engaged with the policymakers, government agencies, and other users and other stakeholders. So these are the three activities Marvi involved in. And this project was carried out in two states of India, Rajasthan and Gujarat. So in Rajasthan, Udaipur district, in Dharta watershed, and in Gujarat, Megraj, Aravali district in Megraj watershed. And both watersheds are about 5,000 hectares in area. And we selected 5 villages in Rajasthan and 6 villages in Gujarat. And both watersheds have hard rock aquifers. So broadly, you can divide aquifer types into two. One alluvial, which is in Uttar Pradesh, Bihar, so it's a Gangetic plain. And then the other states like Rajasthan, Maharashtra, Gujarat, they are dominated by hard rock. And there's a big difference in how the water is stored in alluvial aquifers and hard rock aquifers. So in hard rock, it's more fractures of the rocks where water sits, and then there is connected fractures. So when you dig a well or put a bore, water flows and you get water. Whereas in alluvial aquifers, you have pores in the aquifer material, and water is stored there. And so these are the differences. And the Marvi approach. So generally, there are three sort of groups. One is community, the other one is government, and the third one is science or scientists. And there's a lot of some interaction between government, policymakers, regulators, and people who manage groundwater and the science part of this, but not much connection between scientist, and community, or community and the government. So what and that was really disconnect. So what we tried to do is bring these three together. That's where the work of Marvi was. So work with the science, work with the government, and work with the community to address the complexity of groundwater management. So who were the actors in the or participants in the Marvi project? So researchers like some of us, and these Bijoys or the villagers called Bhujal Jankars, and then the schools and communities, and Gram Panchayat, state and central government agencies. So these were the people we were dealing with. And so what Marvi is in nutshell trying to do is local management of groundwater, improved livelihood, and groundwater sustainability. These were the sort of key focus areas. And so we focused on three aspects: aquifer recharge, understanding the recharge dynamics process, and how the rainfall and the water level in the well fluctuates, and so on. Then we looked at the groundwater use. So, how can we reduce groundwater use through better irrigation methods, better agronomic practices, using crops that requires less water, and then village level engagement. So, involve farmers, schools to monitor rainfall, water levels, and check dams. And so the BGs become very important part of all this. And then by doing all this, the whole idea is to develop this village groundwater cooperatives or village groundwater cooperatives. So it's a group of farmers getting together to develop a cooperative and then recharge and monitor and use in a very cooperative way, share groundwater. So these Bhujal Jankars, there were 25 in Rajasthan, 10 in Gujarat, and each Bhujal Jankar monitored 10 wells. So we had 250 wells in Rajasthan and 110 in Gujarat. And these BJs monitored these wells every Sunday, every week. And so they also had to go through some basic hydrogeologic training in those concepts: mapping, water table monitoring, how to measure water table, how to measure water quality. And so they went through 7 modules. So just think of these are the people who only have class 5 education, at the most class 10, so secondary school, and left schooling probably 10, 15, 20 years ago. And what they have is life experience. And so we worked with them to make them knowledgeable about these concepts. And so what happened was they became sort of local champions, very proud of what they learned. And also they became interface between research team and community. So when we went there, they were always there, already there. And we didn't have to explain to the community or other farmers. They were speaking on our behalf of what we are doing, what we have learned, and so on. So they really felt empowered and valued. So what did we really do in the Marvi in terms of actual hands-on? So we trained these BJs and worked with them on ongoing basis. So it's not just giving the training and say, okay, uh, you do what we have told you and see you in 3 months time or 5 months time, and you keep monitoring and send us the data. No, we didn't do this. We had a lot of hand holding, nurturing their development, and worked with them on weekly basis or sometimes daily basis, and collected groundwater. They collected groundwater depth data, rainfall, water quality, checked them water level, and we also collected some socioeconomic data to understand what people think about groundwater, how, what are the issues, what can be done, what can't be done, like that. And worked with local schools, community groups, and worked with Gram Panchayat and state government. Have explained about what we're doing, what they can do, and develop some tools like, for example, some calculator to Excel type calculator to understand the water balance, my well app to collect data, and some other capacity building aspects. We have developed some teaching resource material, and also at the same time we connected with policymakers at state level, central government level. So all this was really ongoing. And imagine, not just 1 year, 2 year, last 9 years. And so now what we have got is what we started in 11 villages, five in Rajasthan and six in Gujarat. So this Marvi approach has been taken up by the government of India in the Atal Bhujal Yojana, which was launched in December 2019, and is being implemented in seven states of India and more than 20,000 villages. So what we started in 11 villages. So some of the elements are being used in at the that level. So what it means is if we develop a rigorous methodology process, things can change and can be adopted. And still there is a lot of work to be done. And what we have done is a drop in the ocean. There's a lot of many other people are working, and we tried to do something at a village level. So we didn't go for developing a mathematical model and developing some sort of very sophisticated methodology using remote sensing or GIS and all this. But we just worked in a very, very basic level where you can work with the village people, where you can develop the science they can understand, they can use, and that sort of thing. So these are the pictures what these BJs have done. So, for example, they worked on maps, and again, remember these are the people who never went to a university, and but we helped work with them to work out the maps, and they also surveyed the land use, the aquifer type, and they colored these maps where what type of rock is there, what type of land use is there, and then we put them into GIS mapping. And they also gone through this training, what type of rock is there, how to measure rainfall. They were in the classrooms teaching and so on. And these are some more pictures of uh, training in the field. This BJ is marking a particular well, so giving the ID to the well, and then they will come every week. And this is a classroom in the university in Udaipur. And during this particular day, I happened to arrive here from Sydney, and I was interacting and asked some of these BJs what did they feel, and they really felt very proud. And they said, "We never thought we will see a classroom in a university. We left school long time ago. We didn't even finish our high school." So I think what it shows is if you give people chance, if you value them, they can do anything, and that's what these villages have demonstrated. And we had lots of meetings, so we actually didn't show off that we have a PhD or we are any big people. We are just like them, and worked with them and develop that sort of co-working relationship. So more like colleague scientists, but they are citizen scientists, and we are a little bit trained scientists, and uh, and learned a lot of things actually, more learning than some other things you do by um, researching other things. So worked with women group and like that, and I think. It was not a easy journey. So um, we spent a lot of time, and if you see the academic performance, for example, writing papers and all those things, we would have written many more papers if we did some modeling and some analysis and produced nice graphs and maps and so on. But we actually worked with these people, and sometimes it was hard to publish because you go to some journal and they have particular scope, and they say, okay, it doesn't fit in our, because you have the social science aspects and the groundwater science, or some probably don't understand, can't fit because don't have the this experimental replication and those hypothesis testing and like that. But I think what it has changed was it was a very gradual, and in the beginning, uh, we really had to explain to these BJs, for example, very simple things. How many centimeters are there in meter? So I give an example. One of our people working, and these BJs were some BJs reporting water level 28 meters and then 27 meters. Then the person, the facilitators who were in the villages, they start wondering why they are reporting exact values. So they asked the BJs, how come you got the very exact number? They said it's roughly. And we said, explain to them, look, you have to measure to the centimeter. And this is how many centimeters are there. And once they got that idea, they never had any problem. Another instance is they didn't understand the research part. So um, one BJ, I think this is Hariram. So he what he did one time in the beginning, first few months. Um, so he was also taking readings, and one time he took reading, and also we have uh, facilitator in the village called Pralat, and he randomly checks because we wanted to make sure that we have reliable data, and we also put number of sensors in some of the wells so that we get some data and we can analyze, and we can also report some results and meet the funding body requirement that we have done the thing. And so Prahlad realized that the Hariram didn't go to the there was a discrepancy in the what Hariram reported and what Prahlad found. And then so he went to Hariram's home and said, look, Hariramji, there is a problem. What you said is not correct. There's a difference of half a meter because you measured this morning. I also measured after you. And Hariramji immediately realized that he is caught. So he said, Prahlad said, look, Hariramji, we can't have you as a BJ. We really want to, and we can't do this way. And but Hariramji was very adamant that this is a good project and it could help villagers. So he said, I want to continue. What can I do? And he said, we can't. We lost the trust in you. So he said, okay, I can do one thing. Let's go to the temple, and I will take oath that I will not do this again. And from that on day onwards, Hari Ram and all other BJs, I think they got the message, the importance and what research means. And actually, Hari Ram became the champion of all these BJs. And he presented his experience at the National Forum in Nagpur in 2017, this Bhujal Manthan, organized by CGWB, and the minister, water minister, central water minister was there. Gadkariji was there, and he just made a presentation before 2,000 people. So that was the transformation. And this is some example of what these BGs can measure. And what we found out that once they got hang of it, they can be very reliable. We checked with our sensors, we checked with the photos they took of the readings, and they are as good as anybody can be. And again, this is for the whole village, the groundwater levels. And we also measured the check dam water levels. So every day, for example, in rainy season, monsoon, these BJs will go there, monitor the water level, the water depth, and that they will take a picture as well as report the reading, and they were sending back pictures. And we looked at their pictures with the date and time and the reading, picture of the reading, and they were reporting within 97% accuracy. So that's the best you can have. And we did all the water balance of these beaches data, and we developed this balance how much groundwater is there, total water came, the rainfall, the evaporation, and the recharge, and how far that went, and all these things we done. And we even published in international peer-reviewed journal like hydrogeology journal or some other journals. And so what I want to say is, uh, although these BJs are not highly educated, but they are highly reliable, and they can learn and they can understand. We also developed this app called MyWell, available on Android, this Google Play Store, and this way farmers or these BJs can report water level data, rainfall, water quality, check them, and anyone can see what the water rainfall is or well. And it's not just measuring, it starts a dialogue, the conversation between people. So for example, when they measure rainfall and in monsoon season, they say, okay, we had today 18 millimeter rainfall, okay, and then the other day was 29 or something. So they started comparing. And before we started the project, generally people will say how much rainfall, or very good rainfall, or not good rainfall, or they will say enough rainfall to have a runoff on the ground. So those were their indicators. But after this project, they started talking in millimeters, so many millimeters. They started getting a sense. And some of the farmers even related the rainfall amount to groundwater level without using Excel regression modeling. Okay, if we have nearly 50 millimeter rainfall, we expect 3.5 meter rise in water level. This is from their own observation. And they started planning, okay, if we have this much rainfall, this much water level, rise from June to September, we can irrigate so many bigger or hectare of land, and we should limit this or that. So they started quantifying, and also they start having data. So from otherwise you forget, after a monsoon finished, next year or year after, you don't know what was the rainfall or what was, you just have some very vague idea. But with the data available, you start quantifying, and you become internalize the whole science. The ultimate idea is to develop this village groundwater cooperative. So within a gram panchayat, you can have a number of village cooperatives. So where people will recharge, monitor, and based on this monitoring of groundwater, rainfall, and other parameters, you decide how much to use and then share the groundwater. And I believe this is probably the way to go. Uh, any other regulation or any other law of using groundwater probably will not work, or any even technology, people can pass the technology. So we need to follow something like this. So cooperation of the people, they they own the problem, they own the solution, and they manage the solution. That should be the way. So last slide coming to, so key findings: groundwater management need to start at the village level, not at any other level. So we grassroots from bottom up, that will be the way to go. And villagers as BJs can learn how to monitor, understand, and they can take responsibility to collectively manage their groundwater. And if we can replicate this sort of thing in natural resource management, I think we will do a much better job for the future. And we need to engage women. We didn't couldn't get many women participating, but I think this is the challenge, and we need to find ways to do this, because they bring another perspective to whole idea of managing groundwater or water in general. And also we need to really think each village is different, from groundwater availability, from socioeconomic, from some other aspects. So we should not have a one size fit all type solution. We should change a little bit to meet the local needs. And also, groundwater needs to be trust disciplinary. So the technical approach, simple technical approach, is not going to work. Also, we need to trust departmental, trust ministry, because groundwater or water doesn't belong to just one group. It's connected with environment and forest, Jal Shakti or some other department, even rural development department. Groundwater, because that means the development. So it should be a job of everyone. And BJs can collect highly reliable information on various parameters, and they should be connected with gram panchayat. They should be formalized, so it gives them sort of some responsibility and some pride in working in their village for their own people or for their own resources. So that should happen. And there are lots of publication on the Marby website, so you're most welcome. And I think this is the end of my presentation. So welcome any questions if you have.
Uh, Thank you, Professor Basan, for this elaborate and comprehensive overview of sustainable approach on the groundwater management and giving us a thorough insight into Mavi approach. Thank you very much again, sir. We'd like to take some questions. There's a question by Mr. Sharjeel Sofi, and he's asking that from your experience, please tell us what is the most important bottleneck India is facing in the management of groundwater?
Okay, so I think the most difficult aspect we are facing is our groundwater recharge, whether it's natural or artificial recharge, is not coping with the amount of groundwater we take out. And then this is creating also quality problem, because when the aquifers getting empty, and then some of the high heavy metals like fluoride, arsenic, and some other things get mobilized and also brought to the ground, and it's creating a lot of problems. And so groundwater against climate change and all these things happening could be an important buffer. So if there is a less rainfall in particular year, but groundwater is there, you can still save the crop. And so I think to answer this question, I think we have a problem of imbalance in recharge and the use. And also our policies are still technically driven. We need to start from bottom with the individual people, school children, farmers, community, and we put more effort in recharging.
Yeah, there's a one more question by Dr. Asma Tanveer, and she's asking that in Kashmir Valley, majority of the aquifers are in alluvial belt. All apprehensions of getting and have an apprehension of getting polluted because of the high porosity as well as the high water table. So, what could be the possible conservation and management strategies in this regard?
So um, I think whether I'm not very familiar with the groundwater situation in Kashmir, but whatever it is, I think even we have a lot of groundwater in there, it can get exhausted very quickly if we use too much. And also, once the aquifer is polluted, for example, we um, sort of sprayed wastewater or some other polluted industrial water, it can pollute the groundwater. And once polluted, it takes long time to clean it up, and it can stay like that. And that can affect health of people if they are drinking. And so it's a big problem, not only in Kashmir, but you go to Uttarakhand, springs are drying up. And maybe Kashmir also, if there are springs, they probably are drying up because of the climate change, urbanization, less recharge happening, more people using. So, to answer um, her question, I think we really need to start monitoring the depth of groundwater, the quality of groundwater, and also try to understand what are we doing to the groundwater in terms of recharge and what sort of water is going down. And we should consider this as a like gold. I think uh, we should protect at every cost.
There's a one more question by one of the participants. He hasn't identified himself. Uh, it's about virtual groundwater trade of India and how does it affect the current water resources in India?
Can you repeat that question, please?
What is the virtual groundwater trade exports of India, and
Yeah.
how does it affect the current water resources in India?
Yeah, so virtual groundwater, I think it's a again very good concept because things we produce with water, it could be wheat or it could be some other crop, fruit crop, for example. And so it's a very difficult question. It's an international question in Australia also. Okay, we from here the wheat is exported, some other fruits are exported. So some people argue that you are exporting water and like that. So should we not grow a particular rice? For example, there is a particular area in New South Wales where water is used for growing rice, and some people are really questioning whether it is good to grow rice or grow something else. So the idea of virtual groundwater trade export, it can affect, and especially I think if you're growing cotton, for example, irrigated cotton, which I don't think in India is irrigated cotton, but here it's a big issue in New South Wales and in Australia in general. So I think we have to think carefully. Very good question. Should we grow this particular crop or not, based on what how much water we use? Will we be better off growing something else or doing something else? Let other people grow so that we can still save our groundwater. So it's
Yeah,
a
thank you.
trade-off.
Yeah, please continue.
Yeah. So I think um, it's a very important question. It's a policy question at a state level, at a national level, that how should we organize our groundwater use in terms of the crops we grow or things we produce. So we should think about it. And thank you. I think that was a good question.
Yeah, there's a question related to the policies asked by Mr. Sharjeel. It's asking that are policymakers doing enough for the groundwater management, or it is becoming the casualty of Indian politics?
Okay, so I don't think so. I think they started thinking, but again, even state level, I heard some state government is even providing some funds to farmers to drill deeper. That is wrong. I think it's not a groundwater management. It's and same with Punjab, for example. The electricity is free, so if you so that means you can pump out as much water as you can. But I don't think they are realizing in how to control. But some people might be aware that in Gujarat, um, so they started indirectly regulating groundwater use through the supply of electricity. So only supply a certain number of hours, but guaranteed. And that really, some people believe that that worked and was a good policy in that sense.
Yeah,
So
there's a
we need
question.
some more practical, effective, useful policy, I think.
There's one more question by some anonymous participant, and he's asking that what, according to your opinion, is the most suitable and the relevant groundwater remediation technique to be put into practice for improvement of groundwater in qualitative and the quantitative terms in a study area?
Sure. So if, for example, you have a groundwater which is saline, so maybe I think recharging groundwater with the fresh water and not pumping too much water might be a solution. So, for example, in South Australia here, so they collect storm water and put into wetlands, so clean off to some extent, Then they put into the groundwater system through a recharge bore, and that creates a bubble, sort of big bubble, and then that stays on the low quality water, means salty water or some other water, and then you can use this water, pump out that water when it is needed, and for example, for irrigating crops or for irrigating parks or sporting fields and like that. So I think to answer that question, so we need to limit use of groundwater, because as we go deeper, we are concentrating many times the particular pollutants, some salts or heavy metals and like that. So we need to recharge more, and recharge is done by having either artificial recharge or enabling recharge. So in urban areas, for example, instead of having concrete, if you have porous pavers, for example, paving done in, so there are holes there everywhere, and so when rain comes, the water also goes underground and recharges, and the groundwater moves in the landscape. So it can even go to the other areas like where agriculture is. So, and but what is happening as we are doing very much a concrete. So as soon as rain falls, it just runs off and it goes to the ocean or creates some other problem. So the
Yeah,
answer
there's
is
a one
we
more.
need to recharge and we need to um, mm, mm, sort of increase recharge. That will help in the quality and quantity.
Yeah, thank you, sir. There's a one more question by Mr. Ashit Jahangir, Dr. Ashit Jahangir, and he's asking what is the rate of groundwater recharge in confined aquifers, and how can we sustainably manage the groundwater resources in the Himalayan region in the face of a water scarcity due to climatic change?
So the rate of groundwater recharge will depend on the geology of the area, the topography, how long water stays there and gets the chance to infiltrate. So it's very hard to tell what will be the recharge rate, groundwater recharge rate. It will be very site specific, depending upon the soil characteristics, the aquifer, and so on. And for the Himalayan region, I think we need to increase the recharge through, for example, slowing down the flow of water from these mountainous areas. So have more trees, more other things, rather than when water falls, rain comes, it just runs off and goes somewhere else, and then our springs and groundwater is depleted. So we need to facilitate recharge process. Means we need to come back to the nature.
There's a question related to that, but Dr. Shamsul Haq, he's asking like, is groundwater option to us in terms of constrained surface water resources in Kashmir Himalayan region?
Definitely, I think um, because we, with all the climate change happening, even Kashmir, I think we might have some time when surface water is limited. But if we have groundwater as a buffer, um, so we will have access to groundwater, water for drinking, water for growing some plants, agriculture, or whatever there.
Yeah, there's a one more question from the chat box by Miss Ruhi, and she's asking, could you throw some light on the groundwater ownership and use rights with respect to the groundwater conservation?
So again, very good question. So before I answer that question, so we started in Sydney area, Western Sydney, some recharging process, and said, look, we harvest the stormwater and recharge through bore. Now the question comes, because groundwater belongs to the Water Resource Department, and here, if you want to use groundwater, you have to get license, and that license is given to you to extract certain amount of water. Not, it's not like India that if you have the money, you go as deep as you like and you take out as much as you like. There is a limitation. So the question was, they had to change the whole groundwater policy. Okay, if you recharge 100 cubic meter of water, you are allowed to take out 80 cubic meter by pumping. So coming back to the question, so ground who owns the groundwater, or who owns water? Now, if it is surface water, um, traditionally, okay, it's a dam constructed by irrigation department or somebody, so they sort of own and they regulate who gets how much and when and like this. But groundwater being underground, it's very hard to control because it will move to its own way. And also this science of groundwater, especially in hard rock areas, we can't really estimate how much groundwater is there because the size of the fracture. We can roughly say, but it still could be wrong. So I think the best way to answer to overcome this sort of dilemma is the groundwater belongs to the community. And if we give that ownership, then we facilitate that they own the resource, they need to look after, and they need to manage. And I think that may be the way. But if you say, I don't think the governments are good at managing water. Government have funds, they can facilitate, they can help regulate in some way, but water management, especially groundwater management, should come to people. And that's what in last 10 years we have learned.
Okay, I'll take one last question by Mr. Ali Murtaza, and he's asking that ice stupas and artificial glaciers is getting introduced in Ladakh at a large scale now, and how can you see this as an alternative to the groundwater?
Um, Again, I think the hydrologic cycle is changing. So whether it's a good or bad, I think the nature has its own way to come to a equilibrium. So okay, the glaciers are melting, and it will have some other effect on vegetation or biodiversity or the whole water cycle, the flow in the rivers and like that, and then downstream. So I think uh, we shouldn't. Something out in not our control, but as soon as we play with nature, nature has its own way to correct, rectify, and bring the balance back, and that balance could change our lives. And so I'm not 100% sure groundwater is the answer to these glaciers melting. uh, we still should work with the nature. So
Okay,
very difficult question to answer. I think it's
okay.
very complex. There are so many things acting.
Thank you, Professor Basant, for this, elaborate overview of sustainable groundwater management. I, on the behalf of organizing committee, on behalf of myself, thank you very much for accepting to deliver this wonderful talk in this event. Thank you very much. We'll take a break for now, and we'll be joining back by 2 p.m. Request all participants to join by at least 10 minutes earlier, at least by 1:50. Thank you very much.
You're welcome. It was a pleasure.